All right, so I've started recording for activity 3 for Math 284. Essentially, I chose a solving problem rather than a proof problem. I chose problem 3.31. 3.31 is it's uh, it's quite straightforward, but you need to have a certain background knowledge in order to set it up. So the setting up part is probably the hardest part. So we're going to actually look on how to set it up. But first, it's very important to refer to this example right here. So you see where my mouse is. It's you have to refer to example 3.31, and I have it right here written. So basically, the important part about 3.31 is that you have three important aspects. So you have one, the reproduction rate, and you have the adult survival rate, which is a half, and the juvenile survival rate, which is 1/4. You have to take these numbers and take them and put them into a matrix, and then afterwards you have to find out the eigenvalue. That's essentially what you need to do. Now, it sort of sets it up here, but I have set it up in a different way, and I'll show that later. But if you look at the example, and you really have to focus on this example to do the problem, essentially they take this equation here, which is the survival rates, and then they take the equation for reproduction rates, and they turn that into a matrix. Now this part here is the first part of how we solve the problem. The second part is that we use eigenvalue. Use eigenvalues. So again, first part is you have to set it up into a matrix like this, and I'm sorry, that's the first part. This is the first part, setting up a matrix. And the second part is solving using eigenvalues. And then you have to contextualize those eigenvalues. That's sort of the third part. So if we go here, it gives you an idea, and I had looked this up, so I have to reference it, of what to do with an eigenvalue once you're done solving for the problem. So again, I'm going to repeat it one more time because I think it's very important. This problem is essentially three parts. Setting up a matrix, which is something along these lines. So you have survival rates on top and reproduction rates on the bottom. Using eigenvectors, eigenvectors, and then contextualizing that eigenvalue. So if we go here, we have 4 such examples. And it's asking you if the population is stabilized, extinct, or large. So what you need to do here is that you need to find out the eigenvalue, and you need to interpret the eigenvalue using this sort of definition here. So I sort of set the first one up, and then for the last 3, it's a little less set up. But essentially, the way you do this problem is that you set up a matrix. That's part 1. You set up a matrix, and the top part is the juvenile. The top part is the survival rates. So the way I set this up is that I set up a matrix, and I defined A, J, R, 0. A is the adult survival rate, J is the juvenile survival rate, and R is the reproduction rate. And you essentially take your values from the problem here, and you input them into the matrix. I don't think it matters whether or not A or J is here. I think it gives you the same eigenvalue if you have J here and A here. But I like to put A, J, R, 0 because that's the way it's set up on the example earlier. So you have your first part here. That's your matrix. You have your matrix here, and you have to figure out what to do with this matrix. You have your survival rates on top and your reproduction rates on the bottom. The next thing you do, the second part of this this equation, this problem, is you find eigenvalues for A. Now, to find out the eigenvalues, it's sort of straightforward. You take your matrix from the first part, and you subtract it by a matrix that has, I believe this symbol is called lambda. So you have this matrix with 2 lambdas and 2 zeros. And then you find the determinant after you subtract. Okay, so you find the determinant but after you subtract. So we have our matrix, we set up our matrix, we subtract by this matrix here. And this is something that you just have to know when finding out eigenvalues. You have to set up something along these lines right here. So we have an eigenvalues. We have subtracted right here. So we have 1/2 minus lambda, which is you take the 1/2 minus lambda, 1/2 minus 0, which is 1/2, 2 minus 0, which is 2, and 0 minus lambda, which is negative lambda. And then you find the determinant. Now the way I find the determinant for a 2 by 2 is I take AD minus BC. So AD minus BC, if you think the matrix this way, it's A here, B, C, and D. So you multiply AD, that's, I messed up the order, but it's multiplication, so it doesn't matter. So that's A, 1/2 minus lambda, times negative lambda. That's AD. And then BC is simply 1/2, or BC is simply 1, but you're subtracting, so you have minus 1 located here. Now this part, I like to make sure that our coefficients are whole numbers, so I multiply this by 2, and you have this part here. Now you're maybe wondering, how do you solve for lambda here? Well, I use the quadratic formula because I don't know if our lambda is going to be rational or not. And then I use a quadratic formula, but essentially think of this as, think of x as lambda. I input my numbers here. So for example, b, the coefficient of b is negative 1. So negative 1 times negative 1 is 1. B squared is 1. There should be a plus minus here. Then I have 4 times AC. A is 2. C is negative 2. So that's negative 4 times negative 4, which is positive 16. And then you take this number, and this is also very important. You only focus on the positive lambda. This is a mistake. Lambda 2 should be, in fact, negative, because it's a minus square root of 17. But you notice here that you have a 2.56 as part of your solution. Now you have to figure out what this means. And I had to look this up. What it means is that if your value is more than 1, then you're going to have a exploding population. So this population, in the instance where the survival rates are 1/2 for each of the adult and the juvenile, and the reproduction rate is 2. In this instance right here, once we set up and solve everything, we have a population that explodes. It does not stabilize. It doesn't become extinct. It explodes. So it's very interesting how you can use the eigenvalues to figure out if a population, in sort of a contrived example, how a population increases. And then there's some examples of that happening where it stabilizes on BCAD. So there's less of a setup here, but I'll go over some of them here, and then for the last two, I'll explain why. I'll explain why these are large and extinct. So, like I said before, how do we get this matrix here? We get this matrix here by taking our survival rates here and our reproduction rate and setting up into a matrix. That's very important. Survival rates, reproduction rate, you take this right here, where my mouse is here, and you make that into matrix. That's part 1. Then you determine the eigenvalues. This is, you could just commit this to memory, for these problems at least. I'm not sure how it would work on a 3x3 or other sorts of larger matrices, but you can commit this part to memory here, and then it's just a matter of algebra. So you remember your subtraction rule from matrices, a 1/4 minus lambda, 1/4 minus 0, and so on. You figure out the determinant by taking a times d minus bc, and you figure out lambda by using your quadratic formula. Now here's very interesting. You have an example of 1. You have a lambda 1 is 1. So if you ever forget how to interpret these examples, you have to just go here, and it tells you exactly what to do. Now, we're looking for something that's equal to 1. It says right here, and if it's equal to 1, we call it steady state, so it remains unchanged, which is the same thing as saying that it stabilizes, as population stabilizes. I could go over the C and D as well, but it's basically the same idea. We need to take our C. So we have 2 survival rates and a reproduction rate. We put our adult survival rate here, our juvenile survival rate here, our reproduction rate here, and then we figure out the eigenvalue by taking the determinant and subtracting this matrix by this matrix. And then once we subtracted the matrices, we figure out the determinant of this matrix, and then we solve for lambda when this is equal to 0. For this one here, I multiplied it by 12, so all the coefficients were whole numbers. And once all the coefficients were whole numbers, I figured out lambda 1. Now lambda 1 and lambda 2, one's going to be negative and one's going to be positive, so you focus on the positive one. And we have here, we have a lambda 1 less than 1. So lambda 1, go back to your definition, it's going to mean that it's going to decay rapidly and go to 0, which is another way of saying it's going to become extinct. Same idea for D. You should notice a pattern by now, that where if you have the reproduction rates or the survival rates, you turn those into a matrix, adult here, juvenile here, reproduction right here. You get the determinant after subtracting by this matrix, which we've used this matrix for all the previous examples. And then we solve the determinant. We have the determinant right here. I like to multiply by 5 to make the coefficients whole numbers. I solve for lambda by using the quadratic formula. And then lambda 1, which is more than 1, means the population becomes large. So to review, this problem is pretty repetitive because it's essentially asking you to do the same thing 4 times. But the not repetitive part is interpreting the answer. So let me review this one more time before ending. You set it up, if you want to do problems like this, you set up a matrix. You take the numbers given on the problem. You put your adult survival rate here, the juvenile survival rate here, reproduction rate here. You take a matrix, you have your matrix here, and then you figure out the eigenvalue by getting the determinant after subtracting by this matrix. So basically three steps: setting up the matrix, subtracting by this matrix, figuring out the determinant, solving lambda, and then interpreting. That's like 5 steps. So matrix, subtraction, determinant, solve, and interpretation. And sort of this shows this the best. These are just shorter examples of the same thing. But setting up the matrix and doing the second part here this is all algebra. The only problem is the only issue I had when initially doing this is interpretation, and then again you have this as well. So that's pretty much it. There's about 3 or 5 steps you need to sort of memorize in order to do the problem correctly. And if you want to know more, there's a nice website that explains this pretty well that I searched up that explains population growth using eigenvalues here. It does a great job of explaining what I just explained, but it's a little bit more detailed. Let me go here. So that's pretty much it. Remember these 4 or 5 steps, and you're good to go.